Good evening. Yes. Just a second. So, can you able to see the screen? Yes. One second. One second. Yes, Ruchia. Good evening. So, just let me know in the chat box whether my screen is visible to both of you. Just let me know in the chat box. Yes. Okay. Okay. So, I don't have a power supply in my place. So, I did not turn on my video today. Okay. So, kindly let me for today alone. Yeah, Ruchi, I'm fine. How are you? How are you? Yes. Yeah, fine. Okay. Okay. So, guys, yesterday I was dealing with the biomolecules with you all, and among the 6 biomolecules which are given here in this lesson, we have completed the carbohydrates part and the proteins and enzymes, vitamins, nucleic acids yesterday. So, the last biomolecule of this lesson is hormones. Okay. So, what are hormones? They are intercellular messengers. Hormones are intercellular messengers. They pass the message between the cells. Okay. And they are produced by the endocrine glands in your body. They are produced by the endocrine glands in the body. Got it? These are the informations which you should know about the hormones. And steroid is a hormone. Examples of steroids are estrogens and androgens. And again, insulin is a hormone which is made of which is a polypeptide chain. Okay, got it. So moving on to the next part of hormones. The important hormones and their functions we are going to see. So there are three different hormones I'm going to talk with you today. Okay, the first one is insulin. So insulin only maintains the blood glucose level in the body. So glucose is getting converted to glycogen with the use of insulin, and glycogen to glucose again with glucagon. Okay. So insulin is the one which maintains the glucose level, blood glucose level in the body, which we all may be knowing. Okay. So most of the patients are diabetic patients. So they are in deficient with this insulin secretion. Got it? And the thyroxine, second hormone is thyroxine, and it is produced by the thyroid gland, which we all know. And it is one of the iodinated derivative of amino acid called tyrosine. So yesterday we have discussed about the amino acids, no? So tyrosine is an amino acid. The iodinated derivative of tyrosine is thyroxine. So the low level of thyroxine leads to hypothyroidism in a person, and the high level of thyroxine leads to hyperthyroidism. So hypo means you can see in some persons the neck part, it will be bulged out. No, that is hypo. It is because of the secretion of a very less amount of thyroxine in thyroid gland. And hyper, there is no bulging. You can see the person, a normal person. So there is no external symptom. Got it? So this is about the thyroxine. So any doubt in insulin and thyroxine? Insulin maintains the blood glucose level in the body, and thyroxine is produced by thyroid gland, which is an iodinated derivative of tyrosine. There are two types. Low level leads to hypo and high level leads to hyper. So any doubt here? Shall I move on to the third hormone? Shall I move on to the third hormone? Yes. Sandeep and Ruchia, are you there in the class? Yes, steroid. The third is steroid. So steroid is produced by adrenal cortex and gonads. Sandeep, you can hear me, right? Ruchia and Sandeep, am I audible? Just let me know in the chat box if I am audible or not. Students, am I audible? Yes, steroids are produced by adrenal cortex and gonads. And adrenal cortex gives glucocorticoids, which control the carbohydrate metabolism. And there is the other one called mineralocorticoids, which control the level of excretion of water and salt. Which controls the level of excretion of water and salt. So the mineralocorticoids and glucocorticoids, they should function properly. Okay. Generally, all the metabolism in your body takes place in a proper way, and the excretion, everything goes in a good manner. Okay. And gonad in male, it is called as testosterone, and female, we have estradiol. So these two hormones are responsible for the development of secondary sexual characters in male and female. Okay, testosterone and estradiol. They are the responsible one for development of secondary sexual characteristics. Got it? So this is about steroids hormone. And let me summarize from enzymes. So yesterday we have studied enzymes, and we have classified enzymes into two. First is upon class of compounds, and second is based on the reaction. Then in under vitamins, again we studied two category. One is fat soluble and the other one is water soluble. Fat soluble vitamins are A, D, E, K, and the water soluble are C and B, X and B12. Okay. And the third one was nucleic acid. So DNA, RNA were there. TZ and AGCU. They are those nitrogenous base pairs of DNA and RNA. And today, coming to the hormone part, there are three hormones I have discussed with you: insulin, thyroxine, and steroid. Okay. So, any doubt you have here in this biomolecules lesson? Good evening, Devan. Good evening. Students, can you hear me? Hello. 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 Students, can you let me know whether I'm audible to you or not? Yeah, yeah, yeah. Yeah, yeah. Just a second, just a second. Sorry, sorry, your messages was not visible to me. That's why I couldn't see. Sorry, student. Sorry, dear. Okay, fine. So we are done with. Yes, now it's visible. Now it's visible for me. Your messages are visible for me. Yes. Okay. So we are done with biomolecules lesson. And I want all of you to go through the biomolecules lesson, which is very easy, and it is a biochemistry lesson actually. So it will be very easy for you guys. And tomorrow, day after tomorrow, I'll be discussing the question session. Okay, in enable classes. And I want to move on to the next lesson, the very important lesson for class 12 for both NEET and JE. Okay, which is D block element and F block elements. Shall we start with that? Are you all ready? So today we are going to, tomorrow we'll be practicing questions. Tomorrow we'll be practicing questions. Okay, on the whole biomolecule. Tomorrow and day after tomorrow is fully our question solving session only. Okay. So now I'm going to start with the new important chapter called D and F block elements. So my screen is visible to all of you, right? Is my screen visible to all of you? Yes. Okay. So coming to D and F block elements, so there are some technical issues with me today. Okay. Fine. So let me start with the lesson, the D and F block elements. Okay. So first of all, we are going to see the position and general properties of a transition element. So under this particular topic, I am going to discuss with you all the position and electronic configuration of D block element and F block element and some general properties. So you can see the general properties is classified into three parts. I have divided it into three parts. And in the first part, physical properties till oxidation states are covered, and the second part, standard electrode potential till magnetic property. And in the third part, we'll be discussing with the color formation of colored compounds, that is color ions till alloy formation. Okay. So I'll start with the first topic for today's class, that is position and electronic configuration of D block elements. So before moving on to the position, first of all, we should know the definition of transition element, right? So D block elements are otherwise called as transition element. But all T block elements are not called as transition element. Okay, that I'll come to that part later. So now I'll discuss the definition of transition element. So according to International Union of Pure and Applied Chemistry, Transition metals are defined as the metals which have incomplete d subshell, which have incomplete d subshell either in neutral atom or in their ions, okay. So how many d subshells we have? How many d orbitals are there? We have 5 d orbitals, right? 1, 2, 3 and 4. So there are 5d, yes, there are 5d orbitals, and all the d orbitals should not get filled in their neutral state as well as in one of their oxidized state. Okay, means the system, the d orbitals should not get 10 electrons. It should at least get 1 electron less. Okay, so if the system is like that, then it is called as transition metal. It is called as transition metal. Yes, 1 to 9. Number of electrons in the d orbitals, d subshell should be between 1 to 9. Got it? This is the definition of transition element or transition metals. Now the position of the different blocks in the periodic table is on this screen for you. So we all be knowing this. The first two group consist of S block, and 3 till 12 is D block, and 13 till 18 is P block, and from lanthanum and actinium in D block, so two more rows are formed, no? Those are F block. So this is the position of different blocks in the periodic table. Now in this lesson we are going to deal with the D block and F block. So these are the 4D series you can see. So there are only 4 series, 4 rows. Okay. So the first row is called as 3D series. The second row is 4D. Third is 5D, and the last one is 6D. So there is no 1D, 2D and all. There is no 7D also. We have 7 periods in the periodic table, but the D series starts from 3D and ends with 6D. And 3D starts from scandium till zinc. 4D is from yttrium to cadmium. 5D starts with lanthanum and it ends till mercury. And the 6D series starts from actinium and it goes up to copernicium. Okay. So the starting and ending element of each series, they are very important. Okay. So you have to study, you have to concentrate on this and memorize this. Okay, there is no concept here, you just have to memorize this. These are the just informations. So 3D starts from scandium and ends at zinc. Yttrium to cadmium is 4D, lanthanum to mercury is 5D, and actinium to copernicium is 6D. Okay, so any doubt so far? Any doubt you have? No doubt? So I'll move on to, yes. So I'll move on to the electronic configuration. So far we were discussing the position of D block in the periodic table. Now I am going to discuss the electronic configuration of D block. So first let's complete this D block and then we'll move on to F block. Okay, we'll complete all the informations related to D block elements and then we'll come to F block and study all the properties, chemical reactions, etc. etc. Got it? So now we are concentrating only on D block. That too, here on this slide, we are discussing about the electronic configuration of D block, which is N-1, D1 to 10 and N is 0 to 2. Again, a very important thing. Okay, very important thing. So in the question paper, if they are asking this question, so they will confuse you with this number. They'll give N-1, D1 to 10 and N is 2. Or they'll give N as 0. Or here in place of 1 to 10, they may give N minus 1, D 10 alone. Instead of 1 minus 10, they can give 10 alone. Okay. So like this, they'll confuse. So you all have to be very careful. This 1 to 10 and 0 to 2. That is a general electronic configuration of D block. And the minimum value of N should be 4. Minimum value of N should be 4. Then only we will get 4 is 0 to 2 and 4 minus 1 is 3D. 3D 1 to 10. Okay. Because the D series starts with 3, right? So we don't have 2, 1 and 7. So the minimum value of N should be 4. Then only we will get 3. 3D. If you put 3 as a value of n, we will end up with the 2D, right? We don't have 2D. So the minimum value should be 4. And these are the 3D series: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Okay, and the atomic number Z is given to you. It is very easy. It starts from 21 and it ends with 30. Okay, and you can see the electronic configuration for all the 10 elements. 3D1 4s2 for scandium, 3D2 4s2 for titanium, 3D3 4s2 for vanadium. But you see chromium, so we are supposed to get 3D4 and 4s2. We are supposed to get what we are supposed to get for chromium. We should get 3D4 and 4s2, right? So this is the expected configuration. This is the expected configuration for chromium. But instead of this, we are getting 3D5 and 4s1. 3D5 and 4s1. Why? Why the observed configuration is 3D5 and 4s1? Can anyone tell me? So why the observed configuration is 3D5 4s1 instead of 3D4 and 4s2? Yes, very good. It is because of the half-filled configuration. So we have 5 d orbitals. We have 5, yes, Sandeep. Good. So we have 5 d orbitals, and if we put 5 electrons each, the system is half-filled. The system is half-filled, right? So half-filled configurations, and they are more stable. Half-filled configuration and completely filled configurations are more stable than partially filled configuration. So that's why to attain the stability, one of the electron from 4s orbital jumps into the 3d orbital. Okay, since the energy difference between the 3d and 4s, they are of comparable energy level only. So there is no much energy gap between them. So an electron from 4s jumps to 3d to give the stable electronic configuration. That's why we are getting 3d5 and 4s1 for chromium. Okay, and then for manganese it is going in a proper way, that is d5 and s2. For iron it is d6 and s2. For cobalt it is d7 and s2. Nickel 8 and s2. And for copper, you see, for copper, just a second, for chromium it is due to half fill, and for copper it is due to the fully filled configuration. For copper it is due to the fully filled configuration. So what should be the expected electronic configuration for copper? It should be 3d9 and 4s2. But if one of the s electron jumps to d orbital, it attains 3d10 configuration, which is fully filled, which gives the extra stability to the system. So that's why these two exceptions are seen among the 10 elements. For chromium and copper, we are seeing this. Okay, and in the exam, if they are asking you to find out the electronic configuration of copper or chromium, you have to select the observed electronic configuration option. You should not select the expected electronic configuration. Okay, so the observed electronic configuration option should be given. That is the correct answer. So for zinc, you see, for zinc it is 3d10 and 4s2. So any doubt here in the electronic configuration and the exceptions of chromium and copper? Any doubt, students? No doubt. Thank you. Thank you. Now I'll move on to the general properties. So position and electronic configuration, they are clear to you, and I'll go for the general properties part 1. So it starts with metallic property. All the D block metals are good conductors of heat and electricity. All the D block elements are good conductors of heat and electricity. Okay, transition metal, you see, they are conducting the heat. So if we are heating it, in a furnace, it is conducting that particular heat, and it is a good conductor of electricity also. It carries current also. Okay, so there is a transition metal block placed here, and what it is doing, it is taking the current. Okay, so they are the good conductors of heat and electricity. So this is the metallic property, and one more is also there. Those are lustre and hard. So what is meant by lustre? Lustre means shiny appearance. So all the transition metals are having the shiny appearance, and they are very hard. They are very hard. You can see the names here. They are very hard. The screws you can see, we use in our homes. They are very, very hard. Got it? They are the good conductors of heat and electricity, and they have a lustre appearance, and they are very hard. Now coming to the next point, they are more ductile and malleable. So what is ductility and malleability? Ductility is the property in which a metal can be drawn into wires. You can make a thin wire out of, which can be drawn into wires. Transition metals are having that property, which can be drawn into wires, is called as ductility. And using a hammer, you can make a thin sheet of this particular metal, and you can make the material which you want, okay, for your purpose. So that property is called as malleability. Okay, so pushing and making into a thin sheet is called as malleability, and which can be drawn into wires are called as ductility. And transition metal is having these two property. You see, a person is turning, person is bending, that you see, it is malleable and ductile. That's why the metal is bending. Okay, but there are some exceptions. Manganese, zinc, cadmium, and mercury. These four transition elements, these four elements under will not have this ductility and malleability property. Okay, these are the exceptions. These are the exceptions. Just have a note of it. Okay. So coming to the metallic structure, so the five elements which are given to you on the screen, they are having body-centered cubic structure, BCC, and the next five elements are HCP, hexagonal close packing structure, and the four chromium, cobalt, nickel, copper, they are having cubic close packing structure. So these are the crystal structures of the given elements. Okay, they can be crystallized at this particular BCC, HCP, and CCP form. So this is a metallic lattice, which you would have studied in your solid state lesson. Got it? And coming to the next property, melting point and boiling point. So is the metallic property clear to all of you? Yes, Sandeep? Sandeep, yeah. Sandeep, tell me. Yes, you want the slide? Want the slide? Okay. Do you have any doubt here in the slide? Okay, okay. You can note it down. You don't have to draw the picture. Okay. So you know what is BCC, right? So there is a cube, and cube has 8 corners, and all the corners are occupied by a particular element, and the center of the cube is occupied by a element, which are our D block. Okay, good. So now coming to the melting point and boiling point. So in the D block elements, the melting point and boiling point first increases, then it decreases. So you can see the graph which is plotted between atomic number and melting point. So you see the red colored dots are 3D series. This is a 3D series. And the blue lines are 4D elements. And the green line is your 5D element. Okay. So these are the different series. So first, the melting point and boiling point increases for a particular series, and then what happens? It decreases, and then it decreases, and then increases, and it goes on. So why it increases? So you can see in all the series, the chromium group elements are occupying the peak position. In all the series, the chromium group elements are having the highest melting point value. Why? Why they are having the highest melting point value? So to understand this, we are taking the electronic configuration of chromium, which is 3d5 and 4s1, and you can see there are 6 unpaired electrons present here in chromium. How many unpaired electrons? 6. In case of molybdenum and tungsten also same thing. That is 3D and this is 4D and tungsten is 5D. So number of electrons remains same, which is 6. If the number of electron increases, the metallic bond that also increases. Metallic bond strength, we can say. Bond strength increases. So the energy required to break all the 6 bonds will be very high. So that's why the melting point of the chromium and its group members, it is very high. Clear? If the number of electrons are more, then the melting point is more, since the metallic bond strength is more. Clear, guys? Clear for all? Yes. Now coming to the next property, next to physical property, all these are physical properties, okay? The conductivity, conduction of heat and electricity, and luster, malleability, ductility, melting point, boiling point, and now enthalpy of atomization. All these will come under physical properties only. Okay. Now, what is enthalpy of atomization? The energy required to break the bond, and on breaking the bond, a particular molecule will be separated into atoms, right? So that is called as enthalpy of atomization. So enthalpy of atomization also first increase, then it decrease. So chromium is having the highest value again. Chromium, molybdenum, and tungsten. So here atomic number versus enthalpy, energy, that is in terms of kilojoule per mole graph is shown to you, which is there in your book also. And here also chromium is having the highest value because of the same reason, because of the same unpaired electron reason. So if the unpaired electron is more, metallic bond is more. So all the 6 electrons will form 6 bonds, we can say. So the energy required to break all the 6 bonds will be very high. That's why chromium, molybdenum, and tungsten are having the highest enthalpy of atomization. Got it? So there are, let me take like this. There are there are two chromium metals. Okay. Now they are connected with a metallic bond. So since there are 6 electrons for each chromium, there would be some 6 electrons, right? There will be some 6 bonds. There will be 6 bonds. So I have to break all the 6 bonds. Then only I'll get separate chromium atoms. Energy required to break all these bonds is nothing but the enthalpy of atomization. If the number of bonds increases, then the energy required is also increases. If the number of bonds is very less, in case of scandium, you see, in scandium, how many d electrons we have? We have only one d electron, no? So there will be only one bond between scandium. So I have to break just only one bond. So I can break it easily. That's why the enthalpy of atomization of scandium is very less. But in case of chromium, you see, it is very high. Got it? So this is just for understanding purpose, okay? Metallic bonds are due to the delocalization of electrons. Just for your understanding, I have shown it in terms of covalent bond manner. Actually, it is not a covalent bond, it is a metallic bond. Covalent bond is formed by the sharing of electrons, no? But metallic bonds are formed by the delocalization of electrons over the entire lattice, metallic lattice. Clear for all students? Shall I go with the next thing? Shall I go with the next property? Yes. Yes. So the next physical property is atomic radius. So we all know across the period atomic radii decreases. Across the period atomic radius decreases. So scandium, then titanium, then vanadium, chromium, manganese. So what happens? The size decreases across the period. The same is the case with this D block elements also. Okay. So you see here. So the for 3D elements, the green line, green curve you see, the atomic size first decreases till nickel it decreases, or till cobalt it decreases. And cobalt and nickel, they are approximately maintaining a same value, and then it increases. Atomic radius increases from nickel to copper and zinc. So why there is a regular decrease in size and then an increase? That is an exception. That is an exception. Okay. For this particular transition element, there is an exception. So size first increases, then it first decreases, then it increases. Okay. And for 4D and 5D element series, you see 4D and 5D are maintaining the same value. The value of the size are very similar. Actually, while so this is your 3D and this is 4D and this is 5D, right? Left to right size decreases. Moving from top to bottom, the size should increase, right? So if 3D is like this, 4D should be bigger than 3D and 5D should be still bigger than 4D. So this is the trend we are expecting. But while going from 4D till 5D, the size remains almost the same. You can see from this curve. You see the radius, it is almost closer to 15 nanometer only. So why it is approximately same? Why 4D and 5D they are maintaining the similar value? So any idea you have? Any idea you have, students? Because of the lanthanoid contraction, which is there on your screen itself. It is due to the lanthanoid contraction. I'll explain you what is lanthanoid contraction in F block element. Okay. So here after this lanthanum only lanthanides comes, right? So those elements, because of their contraction, so this particular zirconium and hafnium, which is a 4D and 5D element, they will be having similar size. They will be having similar size. So this question is very important. Why 4D and 5D are having similar size? The reason is due to lanthanoid contraction. So you see the 4D series configuration is shown to you and 5D series configuration also I have given. And in case of 5D, the F orbital comes. F orbital comes in between. So on moving from 4D to 5D, the atomic size should increase. Okay, but they are having approximately same size due to lanthanoid contraction. Got it? I'll explain this shielding order and this lanthanoid contraction while discussing the F block elements. So as of now, you just have the concept alone. So can you solve this question? In the series from scandium to zinc, the enthalpy of atomization of zinc is the lowest. Why? Solution is already given to you on the screen. So why, students? So scandium to zinc. So scandium is having one unpaired electron and zinc is having zero unpaired electron. So what is the configuration of scandium? It is 3D1 and 4s2, and for zinc it is 3D10 and 4s2, right? So you see here all the electrons are filled. So there are zero unpaired electron. Here we are having one unpaired electron, and for titanium we have two unpaired electron. So 1 till 9 it increases, and for zinc it is 0. So if the number of unpaired electron is less, enthalpy of atomization is also less, no? So that's why zinc is having the very lowest of atomization. Okay. So any doubt so far? Shall we move on to the part 2 of general properties? Any doubt you have in the physical properties? Okay. So the second property, second general property is the ionization enthalpy. ionization. Yes, Sandeep, thank you. Thank you so much. And ionization enthalpy is the next property. So since the effective nuclear charge increases from left to right, all the effective nuclear charge concepts and all you would have studied in your periodic classification of elements lesson. Okay. So it increases from left to right across the period, and the effective nuclear charge is directly proportional to ionization enthalpy. What is ionization energy or ionization enthalpy? The energy required to remove the electron from an isolated gaseous atom. The energy required to remove the outermost electron from an isolated gaseous atom is called as what? Yeah, it is called as ionization enthalpy. Okay. So now, since the size decreases across the period, ionization energy increases because atomic size atomic size is inversely proportional to ionization energy. Atomic size is inversely proportional to ionization energy. If one increases, the other one decreases. Okay. And on moving down the group, what happens? And on moving down the group, what happens? Moving down the group, size increases. Size increases. And ionization energy decreases. Okay. So this is the atom, and the energy required to remove this particular first electron is called as, first ionization energy. Sandeep, I'll let you know in the next class, okay? I'll let you know in the next class. So Sandeep is thinking of biomolecules lesson while watching over this D&F block lesson or what? Huh? Are you listening the D&F block? Both the lessons are running parallel in your mind. Yeah. I'll tell you. Okay, I'll tell you in the next class. Just remind me in the next class. Yes, Sandeep. Yes. Yes, you're good. You're listening. I know. Just for fun, I said, okay. Fine. So the energy required to remove the first electron is called as ionization energy 1. That is first ionization energy. And the energy required to remove the second electron from the shell is called as delta H2, second ionization energy. And the removal of third electron. For the third electron for this particular atom, we have to go to the penultimate shell, which is the last before shell, right? This is called as third ionization energy. Energy required to remove this particular electron is called as ionization energy 3. And you always remember that the third ionization energy will be very, very high compared to second and first. And if we are removing the fourth electron, then it is a fourth ionization energy. That will be very high compared to third. So why the ionization energy increases while we are moving from the outer shell to inner shell? Because the attraction between the electron and the nucleus increases, right? Since the attraction is more, the energy required to pull out the electron is more, no? That's why the energy increases. Got it? So when you compare the interaction of this particular electron which is there on the outermost shell and this particular electron which is present on the last before shell, that is penultimate shell, and here in this case the attraction will be more, and here attraction is less. The energy required to remove the electron from the more strongly attracted system will be more, no? That's why the last ionization energy is more. Got it? So what are the factors affecting? This is what I was explaining to you, the attraction of electron towards the nucleus and the repulsion between the electron. There is not only attraction, there is also repulsion, you see. So there is an attraction between nucleus and electron. Since nucleus is positively charged and electrons are negatively charged, there is an attraction between plus and minus. And also there is repulsion between the inner shell electron. Since both the electrons are negatively charged, they will repel each other. So these are the factors. Yeah, in terms of distance also you can see the distance between nucleus and electron is very less, or the attraction is more. Both are fine. So there is an attraction and also there is a repulsion. And in addition to these two factors, one more factor is also there, which is called as exchange of energy. So these three exchange energy, if one electron jumps from one orbital and if it places over another orbital, so what happens? It is moving, no? While moving, it loses some energy. That is called as exchange energy. So these three factors are associated with ionization enthalpy. Got it? And you see here, chromium plus is having the highest ionization energy value compared to manganese plus. Why? What is the actual electronic configuration for chromium in its neutral form? It is 3d5 and 4s1, no? And what is the configuration of chromium plus? It is 3d5 and 4s0. So the electron which is present here on this 4s orbital is removed. So it becomes 4s0. So this is it is actually 4s0. It is not 4s1. It is 3d5 and 4s0. And for manganese, what is the configuration? For neutral manganese, it is 3d5 and 4s2. And for manganese plus, you have to remove one electron, and that electron will be removed from 4s orbital. So you'll get 4s1. So this is the configuration. It is 4s1. Okay. So now chromium plus is half fill. Chromium plus is half fill, which is more stable. Got it? Compared to this manganese plus. This is a half fill, but it is also having one electron in 4s orbital, no? If we are removing the second electron, it would get removed from the 4s orbital. Yes, Sandeep? Sandeep, tell me. You have a doubt? Yeah, that's what I'm explaining. So manganese is also half filled, 3d5. It is half filled, but if you are going to remove the second electron will be removed from this 4s orbital only, no, which has one electron. Okay, got it? If I'm going from Mn plus to Mn2 plus configuration, that second electron will be removed from 4s only. So what you will get? You will get 3d5 and 4s0. Then only it is half full and it is stable. Or we can say Mn2 plus is more stable compared to Mn plus. Mn plus is less stable. Is that clear to you now? Yes. Since chromium plus is half fill, so it requires a higher energy. So ionization energy of chromium plus is more than Mn plus because of stable configuration. And the same case between Mn2 plus and Fe2 plus. So this is the configuration of Mn2 plus, in which Mn2 plus is having half filled d orbital. In case of Fe2 plus, how to get Fe2 plus? What is the configuration of Fe? It is 3d6 and 4s2, right? And Fe2 plus will be formed by the removal of these two electrons. So we have 3d6 and 4s0. So you see, 3d6 means it is partially filled, no? 3d6 means it is, I'm sorry, there is some mistakes over here on the slide. It is 4s0. It is 4s0. And here it should be 4s0 here. And we should not have electron, and another electron will be here, and it should be 3d6. It will be 3d6. Got it? So this is the configuration of Fe2 plus, and this is the configuration of Mn2 plus. Mn2 plus is half filled, and Fe2 plus is partial. So half filled configurations are more stable compared to partially filled, and that's why Mn2 the highest ionization energy value compared to Fe2 plus. Okay, Fe2 plus 3d5, 4s1, 3d5. It can have both the state, but mostly it will be present in terms of 3d6 and 4s0 only. Okay, it will be present like this one. Got it? It can have 3d5, 4s1 configuration also to attain the stability, but manganese only occurs in that form. Not manganese, chromium occurs in that form. Since one of the d orbital is vacant there in case of chromium, we are shifting one 4s electron to the empty orbital, d orbital of chromium. In case of iron 2 plus, you see there is no vacant orbital. There is no empty d orbital in case of iron. So the electron shifting may occur, but if an electron is getting shifted from this orbital to this orbital, we will get a configuration which you have asked, that is 3d5 and 4s1, right? But the electron has to go from this orbital, and it is already bonded. It is already there in the orbital which contains one more electron. So there will be some interaction between these two electrons. Got it? There will be some attraction between those two electrons. It has to overcome that particular power, and then only it can jump to this particular 4s orbital. That is highly impossible. So that's why 3d5 and 4s1 configuration is not possible for iron. Got it? Yes. Now coming to the next property, which is called as oxidation state. So I think we can discuss this oxidation state property in the next class. It's already 4:56 students. You have to get ready for the next class, no? Shall I continue with the oxidation state, or shall I continue today or in the next class? Tomorrow. Okay. Okay then. So what we have discussed today? What was the first topic under this lesson? The position. So the position and electronic configuration, all of you have to go and study again. And secondly, we are discussing the general properties, which are mainly your physical properties. So what are the physical properties we have discussed? The metallic, all types of metallic properties we have discussed, and the atomic size, all the melting point and boiling point property. Okay, atomic size or atomic radius. Yeah, ionization energy and enthalpy of atomization we have studied, and all these 5 properties. They are ductile, they are malleable, okay, they are the conductors of heat and electricity. Everything comes under this metallic property. And melting point, boiling point, the remaining 3 we have discussed. Okay, so you have to go and study all these properties which we have seen today, and then only you have to come for the next class. Just finish studying and then come. Okay, fine. So no doubt. If you're having any doubt from this class, you can let me know in the chat box. You didn't study before the next class, don't hesitate to join, okay? You join the class. Try to study before the next class. So any doubt? No doubt, students? Okay, then I'll meet you in the next class. Yeah, Sandeep? Yes, Sandeep, tell me. Yes, tell me. Where can you see the recorded class of Avanti? Okay. You can see it in the channel, no? YouTube channel. I think only enable classes are there in the YouTube channel. Okay, I'll discuss with the team and I'll let you know on Monday. Okay. I'll let you know on Monday. I'll discuss with the team and I'll let you know on Monday. Is that fine? Yeah. We have the recorded videos and I'll let you know with my team and I'll let you. Got it? You can see the recorded class. It is not only live, we are recording it. You can see it, so that I'll let you know on Monday. Any other doubt? Okay, Sandeep. Thank you. Bye-bye.